Hello, everyone. In this video, I will be covering the common fate model, where we will simultaneously estimate both dyadic and individual level pathways. So if you are unfamiliar with the common fate model, I would recommend watching my common fate demonstration in either M plus or Lavaan that you can find on my channel. And if you have seen those videos or you have some passing familiarity with the common fate model, this is an extension of that, where we will also model individual dynamics within the context of the common fate model. And so just before diving into Lavaan and diving into R, when we think about the common fate model, we are estimating shared variation between between two dyad members, two partners. In this case, we'll be considering heterosexual couples. So we will be modeling shared variation in relationship mindfulness and shared variation in relationship quality. We typically in the common fate model want the variation to be around 50% or higher, which is indicated by factor loadings on the latent constructs of about 0.7 and higher. All right. And so that's essentially telling us that there's roughly the same amount of variance at the individual level and at the dyadic level. But oftentimes, we will have loadings around just above 0.70, which would indicate that roughly 50% of the variance or somewhere in there is modeled at the dyadic level, which means there's also 50% of the variance that is not explained at the dyadic level, and there's individual variability. So in the common fate model, we are not capturing that individual variability, but what we can do is do some sleight of hand trickery that you that may have seen in other models, such as the latent growth curve with structured residuals. We will implement phantom variables, and we will turn the residuals that we normally see in the common fate model, and we're going to be able to use to estimate regression coefficients among those residuals. Because if we think about what the residuals imply within the common fate model, is that it's all the variance that is not accounted for at the dyadic level. All right. So when we think about that, that's where our individual variability lies. There's also going to be measurement error, testing conditions, and all those other things that contribute to variability. But a lot of that information that's traditionally discussed as, again, just error, random error, in the common fate model is actually individual perception. And so increasingly, scholars are recognizing that there's actually a lot of really valuable information within the residuals. And so what we are going to do is we are going to model that individual variability, again, using phantom variables. So before jumping into the syntax, I just want to give you a general perspective on or a visual representation of what our model will look like. And this is going to be our model where we have our two latent variables and we have our regression coefficient connecting them. And then each of them is indicated by dyad member 1 and dyad member 2. And so we have our factor loadings, which again, we will be constraining to 1. I'm just indicating them through lambda 1 and lambda 2. And then we have these phantom variables that we will be implementing. And that's where we will be estimating gamma 2 and gamma 3. And so what gamma 2 and gamma 3 represent are regression coefficients, or accounting for an association within a person independent of the dyadic level process that is occurring. And so one of the cool things about modeling residuals in this way is it will not impact our regression coefficients at the dyadic level. Because once those are estimated, that's where we get our residuals, and then we are transforming those residuals into meaningful pieces of information. All right, so again, implementation of these procedures should not affect your parameter estimates at the dyadic level. Another thing that you may notice is that we, on the endogenous side, we have two error terms, E1 and E2, but we do not have those error terms on our exogenous side. So if you recall some of the assumptions of OLS regression and structural equation modeling, the distributions of our independent variables are fixed and known, which essentially means that they are measured with perfect reliability and without measurement error. So that is the assumption that we are employing every time we run a regression and every time we are running a structural equation model. And we are just extending that assumption to this type of model. So we do not need an error term on this on the exogenous side of these variables. All right, so I will shift us back over to Lavaan. And here is the syntax for the model. And so, so we have the common fate model, and I called IND1. It's with the individual parameters, and it's going to be the first model. We will be testing several models. And so this will be the very first one. And so this is going to be standard syntax for constraining factor loadings. And this is probably familiar to those of you who have seen the common fate model before or have watched my other videos. So we throw a 1 star in front of all of the factor loadings in order to constrain them to be 1. All right, so that's going to be standard procedure in order for us to identify our model, because if these were freely estimated, we would have negative degrees of freedom and our model would be under-identified. And in this situation, our model will be over-identified by a degree of freedom. All right, so this will be, again, this will be identical to the traditional common fate. And so the second aspect of the model, the part of the model that is probably going to be new to a lot of people is the implementation of phantom variables. All right, so phantom variables were introduced in the early to mid 1980s. I think in 1983 was one of the first papers on phantom variables. And they were initially created for Lisrael, because there were lots of nonlinear constraints that people had to place in Lisrael on their model. And that created a lot of estimation problems. And so people had to make a lot of choices, a lot of sacrifices back then, because computational power wasn't necessarily where it is today. And phantom variables were a way of doing that. And now, 30, 40 years later, we are now using phantom variables in order to estimate leftover information that we have from our primary models. And so the way we are going to specify our phantom variables is they are going to be specified as latent, which means you will see the equal tilde sign. And then you will see I have created one phantom variable for each observed indicator in this model. And you will also notice that the factor loading is constrained to be 1. And so this is for identification purposes, because the phantom variable on its own, we need to kind of pin it down somewhere. And so we're actually going to do that by one, fixing that factor loading to be 1. And then, as you'll see down here, we are going to fix those residual variances of those indicators to be 0. All right. And so we're going to do that for each one. So I've named each one I've included IND at the beginning for individual. So it's individual perceptions. of couple satisfaction index, CSI, and then M is for male. So that is my coding scheme. And I have I have the observed variable that's actually in my core data set as the indicator. And again, that factor loading, that lambda is fixed to 1. And I do that again, for each of the variables on both sides, both endogenous and exogenous. And then next, I'm going to fix the residual variances of those observed indicators to be 0. Again, this is also for identification purposes. All right, so essentially what I'm going to be doing is I'm fixing the residuals of the observed indicators to be 0. So of the variables that are actually in our data set, because I want to push that information that would have been in the residual variance of the observed indicator into the phantom variable. So I want to fix those to be 0. All right. And so those model constraints are a way of kind of how I think about it is how regulating where information can be sent and where it is stored. And again, constraining those residual variances to be 0 allows us to push some information into the phantom variable at the individual level. All right. So the next part is going to look identical to existing syntax with the common fate model. And this is going to be our dyad level regression coefficient, where we are having relationship mindfulness predict variation in how happy couples are, and more specifically, how happy heterosexual couples are. And so this is going to be in that diagram I showed you, this is going to be gamma 1. So in this one, this is going to be your gamma 1. And then down here, your IND CSIM with IND RMM men is going to be your gamma 2. This is going to be this coefficient right here. And then you also have the individual for females, and that's going to be your gamma 3. That's going to be down here. All right. And due to some assumptions and defaults that Lavaan makes, you will need to be specifying lots of covariances to be 0 in order for your model to effectively run. And so I fixed the covariances between the RMM dyad and the observed indicator with the individual indicator, or the within person indicator for all 4 of them. All right. And then I also fixed the covariances of between the individual indicators to be 0. So if you all are familiar with the actor-partner interdependence model, you might be thinking, well, why are we doing that? If we're estimating individual parameters, we need to add in those residual covariances because these are non-independent data. And so within like an APIM framework, that would absolutely be the case. But you'll actually notice in the diagram, I don't have them here. And that is because if we think about what the common fate model, how the common fate model is modeling non-independence, is through shared variation in the latent variables. So the residual covariances in the APIM and the variances within the common fate model are serving the exact same purpose. And so the interdependent nature of husbands and wives in this example is already captured. And so we're actually going to presume that the covariance here and the covariance here are 0, because that's an indicator of the non-independence, which again is already captured in these latent constructs. All right. Likewise, you will also see that I have no partner effects specified in this model, but I will go into that in just a little bit. So let's go ahead and run this. This model takes a little bit longer to run than others. We can go and take a look and see what we get. All right. So you will see that we have a single degree of freedom. So again, if you've been following me, you will hear me drone on about how the RMSEA tends to be quite biased in low degree of freedom samples. And so again, that's one of the fit statistics that I will just largely ignore. Either here you're going to get exceptional fit, where your CFIs, your TLIs, your MSCAs, your SRMRs are going to be um, uh, at the highest or lowest value, depending on the statistics. So your CFI and your TLI will almost always be close to one, or in your RMSE and SRMR will be closer to zero, or you will get your CFI will generally behaves fairly well in these models. You'll probably almost always get something around 0.95 or above. Your TLI can be very finicky. I've seen it range, in the 0.7s with models with 1 degree of freedom. And I've seen RMSEAs of 0.11. And I've seen SRMRs of 0.08 or 0.10 in these 1 degree of freedom models. So really take it with a kind of a grain of salt and consult your residual matrix and all those other ways of evaluating model data fit. So here is our latent variables. And as you will see, we have our observed variables being loaded onto the common fate constructs. And then we have our common or our phantom constructs right here. And so you will notice that RMM and CSI, they load quite well onto the common fate latent constructs. Our factor loadings are above 0.70 for all 4 of them. So we are in really good shape in terms of estimating and staying true to the essence of the common fate model. So we can scroll down, and here we will get our regression coefficients. So here is our dyadic level regression coefficient. So a 1 standard deviation unit increase in dyadic relationship mindfulness yields a 0.44 standard deviation unit increase in relationship quality or relationship satisfaction at the dyadic level. So we have a pretty strong regression coefficient. So here we see our individual estimates. And so these are the within person estimates that are independent of the dyad level estimates, okay? And so we have male reports of relationship mindfulness are marginally associated with higher levels of relationship quality. So how I would interpret that is, well, we're going to say, pretend this is 0.047. I'll interpret it, with assuming significance. So men who are higher, who have higher levels of relationship mindfulness independent of relationship mindfulness that occurs between them and their partner also tend to report being happier in their relationship with their partner. And those perceptions are independent of what is happening or what is shared with their partner or with the male's partner. All right. And so regarding the female within person effect, we do not find anything. So it does not look like women their unshared perceptions of relationship mindfulness are associated with their unshared perceptions of relationship quality. And so that is how you interpret those coefficients. You'll see all the covariances that we have constrained to be 0. I am newer to Lavaan, so I'm still working my head around it. So in M+, we have a model equals no cove option that automatically sets these to be 0 and all covariances to be 0. And in Lavaan, I have not identified such an option yet, but it may exist or may soon exist outside, but it is outside of my awareness. So if that does exist, that would actually be a great help if someone could point that out. All right, so we have our intercepts, which again, don't really care a whole lot about within structural equation modeling unless we move into growth modeling. And then we have our R squareds. So we are accounting for just under 20% of the variance at the dyadic level for relationship quality. And we are accounting for 3.4% of the variance in males' individual perceptions of relationship quality and 1.4% of the variance in female reports of relationship quality, independent of what is shared between the dyad. So this is the basic common fate model with individual parameters. To the best of my knowledge, it doesn't have an official name. So I think I've just been kind of describing calling it the dual level common fate model, where you're estimating individual level and relationship level processes. I've also seen it kind of described as just a common fate with individual parameters. But to my knowledge, and it might be out there, there is not like an official name. If we think about like the latent growth curve with structured residuals, which does a similar process in a univariate and bivariate growth process, it doesn't have that name that the structured residuals have. All right, so that is the first analysis, and so the second analysis that I'm going to run is a little bit contradictory to what I've already talked about, but it will hopefully provide additional insights and hopefully promote thinking and different types of statistical tests you can run within your model. And so the primary difference within this model is that I'm going to constrain I'm actually going to add actor and partner effects. And so, as I talked about before, I don't add partner effects into the original model. And that is because, again, the covariance should be already accounted for in that latent variable space. And so we wouldn't necessarily think that there are partner effects. And I would hypothesize that there probably are not partner effects. But what you might want to do is you might actually want to estimate the partner effects, because maybe that will provide more precision or more accuracy in those within person actor effects, right? So we would expect those partner effects to be really, really close to zero, if not zero themselves. But as you already saw, that we actually have a p-value as p equals 0.057. And I kind of interpreted it as if it were significant, so it was 0.047. But if we add in those partner effects, that p-value could shift. That could move from significant to non-significant. And so then you would formulate different substantive conclusions. And so there is the possibility that although the partner effects are small and not likely to be significantly different from zero, they may actually impact the substantive findings that you might make had you not estimated them. And then you'll have to theoretically justify whether or not that's which way to go. Do we test the partner effects because we want to estimate those small effects and that might make a difference? Or is there no theoretical justification? Just know that that option is available to you. All right. And so we're gonna do that. And so we're gonna go down here to the third model, and you will see here that everything else up to this point is exactly the same. All right, so nothing has changed in this part of the model. So if you are following along with me, you can copy and paste. As a matter of fact, that is how I created this model. I just copy and pasted the full first model, and I just added in a couple of parameter labels. And you will see that right here. All right, and so we have individual couple satisfaction for males being predicted by individual relationship mindfulness for males and females. All right, and the same thing for females. But if you may have noticed that we only had 1 degree of freedom in our original model. So if we are going to be requesting 2 additional parameters being estimated, those partner effects, then we need to find those degrees of freedom somewhere in the model. So what we are going to do is we are going to constrain these the within person effects for male and female to be equal, indicated by this A1 star. We have this label that is the same for both of those within person effects. And then we have the same for the partner effects. So we are constraining those actor and partner effects to equality across dyad member. And that is essentially the only change that we are making in this model. All right, and so we can go ahead and we can run this one. All right. So again, we're going to have 1 degree of freedom again. So that will not change. We'll scroll down. We're going to skip over the fit indices. And we are just going to look at those actor and partner effects. All right. And so we are now looking at right here and right here. And what we'll notice is that that these effects are constrained to be equal, and now they are nowhere near significance. All right. And if you recall from the previous model, actually, we can actually go up, that we had the effect sizes of those within person parameters. They were, as soon as I can find it, they were not all that far off from one another. So you can see 1.07 and 0.096, and you can see 1.85 and 1.1 or 0.119 or 12. Not all that big, not all that big. Not the difference between them isn't huge. We would likely be underpowered, and we would not be able to detect this difference. And so constraining them to equality probably doesn't do a whole, is probably not going to do a whole lot of harm within the model. I think that's probably a fairly reasonable type of assumption. And if it's not, you'll see it manifest in that chi-square value. All right. And so we'll scroll down here to our results. I saw some red ink. We'll just take a look at that. Okay, that's just the LRT test, which we can ignore. And here that you will notice that, again, both of them are non-significant. So, by including those partner effects and constraining them to equality, then there is no significant within person effects, right? So the third model that we will run is going to be kind of an extension or a hybrid of actually both of the models that we've covered thus far. And so what we can actually do is that rather than kind of jumping to straight from the individual effects to having actor and partner effects at the individual level, we can actually simply just constrain the actor effects to equality. All right, so those two within person paths, gamma 2 and gamma 3 from the diagram, these two, we can constrain them to equality without estimating the partner effects that are not shown in this diagram that would go from P2 to P3 and P1 to P4. So we can just simply constrain those actor effects or those within person effects to be equal. And then we can conduct a likelihood ratio test in order to see if our restrictions that we are imposing on the model are significantly worsening our model's capacity to reproduce the characteristics of our data. All right. And so what we can do is we can take a look at our model. And we can, actually, I just noticed an error in the syntax. So we will that, and we will actually we can rerun that. This model should be accurate, but that third model we will have to take a look to see if there's any major differences. There shouldn't be, because again, those partner effects should be non-significant. All right, and so what we have here, actually, let's just clear that out so we know what we're dealing with, and we will run this model. Make sure everything is in place and everything looks good. And we'll run that. All right. So what we are going to do here, I found actually one more syntax error. I forgot to include that parameter constraint. So we can we'll call it we'll just call it E1. E1 star. We'll just add that in. And then we'll add that in. And what this is doing that's constraining these within person effects to be equal. Okay. So we will go ahead and we can run that. And then these should be nested models where you will get a chi-square difference test. And that's what we are getting down here. All right. And so we should have, again, 2 degrees of freedom. We had one in the baseline model, and then we had one we gained 1 degree of freedom by constraining those within person effects to be equal. And we still have a non-significant chi-square. And so this tells us that, again, just by eyeballing it, with the critical ratio, or the critical value, I should say, of the chi-square distribution at 1 degree of freedom being 3.84, this is non-significant. So I can tell you right now that constraining these effects to be equal does not cause harm to the model. But what it is doing, it's not doing exactly this, but it's kind of creating like a dyadic average of those slopes between the male and the female, and it is constraining them to be equal. And as you can see, they are actually equal, both significant now, right? And so what we did is, by constraining them to equality, that male effect was kind of nearing significance, but that female effect was not really all that close to being significant. I think that the p-value was around 0.20 or something like that, so not really all that close. But when we kind of tell those pathways you have to be identical, they're actually accounting for a significant amount of variation within your model. And so this is one of those times where, as the researcher, you're going to have to make an evaluation of, do I have a theoretical reason to believe that men's reports of relationship quality, outside or independent of what's going on at the dyadic level, is the same, that effect on relationship quality is the same as in women, right? Because if you theoretically believe that those equality constraints are appropriate, then this is the model that you would choose. But if you are thinking that relationship mindfulness might have a different effect on relationship quality than across men and women, then you will actually need to use the unconstrained model. And so you will get kind of funky results like this fairly often, especially when you're using phantom variables, because even though in our model, it's a relatively simple model, but you tend to see your standard errors get exceptionally large in these when using phantom variables, because there's a lot less precision in our estimates, and you will see that particularly within like the raw random intercept cross-leg panel model and the latent growth curve with structured residuals that both employ phantom variables, and you will see standard errors get to be a little unwieldy, where you'll have a parameter estimate of 0.52 and a standard error of 0.40, and it'll be non-significant because again, there's a lot of imprecision there. But essentially, this is the common fate with individual parameters and a couple of other uh, extensions of that, other things that you can constrain to equality to elucidate your hypotheses and to provide some more nuance to the things that you are studying. Right. So before we end, we are just going to rerun that third model because there was a small typo in the fit statistics where I was getting the fit stats for a different model. All right. But again, we have again 1 degree of freedom. Again, this is where we have the actor and the partner effects in the same model. And they are constrained to equality, so our degrees of freedom don't change. But essentially, we are getting, again, very, very similar results, and it doesn't look like the syntax error was very costly. So the only major difference that you will notice compared to the other models is look at the explained variance within those individual parameters. They got significantly higher. Previously, this was around 3%, and this was around just under 1.5%. So constraining these, including the partner paths and constraining the actor of paths and the partner paths to be equal, did shake up the amount of variance accounted for, but again, none of them were significant. So that's something to kind of play with. And again, in most cases, most of the time, there will not be a rationale from my perspective in order to estimate those partner effects because the covariance is already accounted for in the latent variables, and that can actually send shock waves throughout the rest of your model, as you can kind of see here. That our standardized effect at the dyadic level actually changed because we are estimating those partner effects. So be very careful with estimating those partner effects, because some of that covariation that's occurring between the dyads, some of that non-independence is actually being sucked up by those partner effects, which is why you see the explained variance go up and the parameter estimates at the dyad level decrease or go down. But if you were actually to compare the parameter estimates in the model of the very first model that we ran, this one up here, with the second model, then our parameter estimates should be identical. Right, we'll do that as our final kind of test here. Here in this video, just to demonstrate that. All right, so this is our fit 2 model. Yep. And then up here we should have our fit 1 model. All right, there we go. So let's go to those parameter estimates. So we have 0.438. I'll go a little slower. 0.438 here. And then if we scroll down, drum roll please, 0.439. All right, so there's a rounding error difference when these effects are constrained. But as you noted, when you are estimating those partner effects, it sends shockwaves and ripple effects throughout your model. They can be included, but again, there needs to be a strong theoretical rationale for that, because again, you are accounting for mutual influence, and so that's going to dampen the dyadic effects or what's happening at the relationship level. Hopefully this video into the nuances of the common fate model and some of the different ways that you can test and constrain paths to equality was helpful. And as always, using theoretically derived research questions is paramount.